July 4th, 1974. Pacific Ocean. 16,500 feet beneath the surface, a Soviet nuclear submarine lies broken in 3 pieces on the ocean floor. The K-129 carrying nuclear warheads, missile guidance systems, and codes that could shift the Cold War's balance of power. Every salvage engineer in the world agrees, lifting 2,000 tons from such crushing depths is impossible. The water pressure alone would snap any cable system ever built. Naval doctrine states that deep-sea recovery maxes out at 10,000 feet. Anything deeper remains forever beyond human reach. But 3 miles above the wreckage, the Hughes Glomar Explorer holds position with computer-controlled precision. Inside the ship's classified operations center, 35-year-old Sherman Wetmore watches telemetry screens as his impossible creation, a mechanical claw nicknamed Clementine, descends through the abyss on the longest pipe string ever assembled. The CIA had approached him 2 years earlier with a challenge that defied every principle of marine engineering. Soviet surveillance ships circle nearby, convinced they're witnessing a routine manganese mining operation. They have no idea they're about to witness the greatest intelligence theft in Cold War history. One engineer had refused to accept impossible. The briefing room at CIA headquarters carried the stale scent of cigarette smoke and classified anxiety. July morning light filtered through reinforced windows as Deputy Director Carl Duckett spread grainy photographs across the mahogany conference table. Sherman Wetmore, Global Marine's heavy lift operations manager, studied the images with the methodical precision of an engineer who had spent 11 years turning impossible deep-water projects into routine operations. USS Halibut took these photographs 3 months ago, Duckett explained, his voice carrying the weight of national security. Soviet Golf II class submarine, designation K-129. She went down in March 1968 during a patrol mission, 16,500 feet of water, Pacific Ocean, northwest of Hawaii. Wetmore lifted one photograph closer to the fluorescent light. The submarine lay in 3 distinct sections on the abyssal plain, bow section intact, middle section with sail and missile compartment partially collapsed, stern section separated by roughly 200 feet. Even through the deep-sea camera's distortion, he could see the massive scale of the wreckage, 2,000 tons of Soviet steel resting where no human had ever attempted recovery. Every engineering firm we've consulted says it can't be done, Duckett continued, watching Wetmore's face for any sign of the same verdict. Westinghouse, General Dynamics, Newport News Shipbuilding, they all reached identical conclusions. The deepest recovery ever attempted was Trieste II, pulling up a satellite capsule at 16,000 feet, and that took 3 attempts for a 300-pound object. Wetmore set the photograph down and reached for his slide rule. The numbers formed a crushing reality in his mind. Lifting 2,000 tons from such depths required a pipe string nearly 3 miles long, each section rated for massive tensile loads. Water pressure at that depth reached 750 pounds per square inch, enough to implode conventional equipment like a crushed aluminum can. Dynamic positioning systems would need to hold a massive ship steady within yards while managing ocean currents, surface weather, and the immense stress of a lifting operation spanning hours. What makes you think Global Marine might see this differently? Wetmore asked, though his mind was already racing through unconventional approaches. CIA Project Director John Parangoski leaned forward, his fingers steepled in the gesture of a man who had overseen the most sensitive reconnaissance programs of the Cold War. Because you pioneered dynamic positioning for Project Mohole. Because you've pushed the boundaries of deep-water engineering further than anyone in the industry. And because this isn't really about engineering. Parangoski slid another folder across the table. Inside, intelligence assessments painted a strategic picture that made Wetmore's pulse quicken. Soviet naval activity suggested they were developing submarine-launched ballistic missiles with 1,500-mile range. Current American intelligence estimated Soviet submarine technology lagged behind U.S. capabilities by at least 5 years, but the K-129's guidance systems could reveal whether Moscow had achieved targeting precision for mid-ocean patrol stations. The submarine's missile compartment contains navigation computers, targeting algorithms, and nuclear warhead designs, Parangoski explained quietly. But more importantly, it contains codebooks and operational procedures that could reshape our understanding of Soviet strategic doctrine. Wetmore studied the technical specifications. Golf II-class submarines carried 3 ballistic missiles, each with nuclear warheads designed for targets 1,500 miles inland. If Soviet submarines could launch accurately from mid-ocean positions, they could strike American cities while remaining virtually undetectable. The K-129's guidance systems would reveal whether this capability was operational or theoretical. The water pressure alone would crush any conventional capture system, Wetmore said, thinking aloud. Standard salvage cables would snap under load. Submarine-based recovery lacks the lifting capacity. Traditional ship-based winches can't handle the pipe string length or maintain position accuracy. But even as he voiced these objections, his engineer's mind was exploring alternatives. Project Moholy had been abandoned in 1966, but its innovations in deep-water stability and precision positioning had pushed global marine decades ahead of competitors. The project's computer-controlled thruster systems could hold a ship nearly stationary above a target thousands of feet below. If those systems could be scaled up. Duckett watched Wetmore's expression shift from skepticism to calculation. We're not asking you to recover this submarine through conventional methods. We're asking you to invent new ones. The Soviets monitor all major salvage operations, Wetmore pointed out. Any attempt to position recovery equipment over that site would trigger immediate investigation. Which is why this won't look like a recovery operation, Parangoski replied. Howard Hughes has agreed to provide cover through his business empire. Deep-sea mining for manganese nodules, perfectly legitimate commercial venture. His companies answer to no stockholders, require no SEC oversight, generate no public scrutiny. Wetmore felt the paradigm shift crystallizing. This wasn't a salvage operation constrained by conventional limitations. This was an intelligence theft requiring revolutionary engineering disguised as commercial mining. The technical challenges remained staggering, but the strategic framework had changed everything. How much time do we have? Wetmore asked. Soviet naval intelligence suggests they're planning their own recovery mission, Duckett replied. Current estimates give us 18 months before they develop the capability to return to the site. The room fell silent as Wetmore absorbed the implications. 18 months to design, build, and deploy the most complex deep-sea recovery system ever attempted. 18 months to prove that American engineering ingenuity could achieve what Soviet doctrine considered permanently impossible. 18 months to steal 2,000 tons of submarine from the bottom of the Pacific Ocean while Soviet surveillance ships watched every move. Parangoski closed the folder containing the strategic assessments. Mr. Wetmore, we're not asking you to salvage a submarine. We're asking you to steal one, and the Soviets can never know it happened. The status quo had permanently shifted. This was no longer about marine engineering. This was about proving that democratic innovation could overcome any technical barrier the Cold War presented. November 1971 brought Sherman Wetmore to the sprawling shipyards of Long Beach, California, where Howard Hughes' latest venture was taking shape with the precision of a military operation disguised as commercial ambition. The Hughes Glomar Explorer rose from the construction dock like a technological cathedral, 618 feet of revolutionary marine engineering that would either prove American ingenuity could overcome impossible odds or become the most expensive failure in intelligence history. Wetmore stood beside the massive hull opening that would define the entire operation's success or failure. The moon pool stretched 200 feet from bow to stern, an enormous center well that could be sealed off from the surrounding ocean once a captured object was pulled inside. No ship in maritime history had ever been designed with such an opening. Naval architects had initially declared the concept structurally unsound. The hull breach would compromise the vessel's integrity in heavy seas. But Wetmore's calculations proved the reinforced steel framework could maintain structural strength while providing covert recovery capability. The dynamic positioning system represented the first of 4 integrated breakthroughs that would make the impossible attempt feasible. Computer-controlled thrusters mounted beneath the hull could hold the 50,000-ton ship nearly motionless above a target 16,500 feet below. The precision required was staggering, maintaining position within 100 feet, while ocean currents, surface winds, and the massive stress of lifting operations threatened to push the vessel off target. Wetmore had adapted the technology from Project Mahol's deep-water drilling systems, but scaling it for submarine recovery required innovations that pushed 1970s computer technology to its absolute limits. The heavy-lift pipe string presented even greater challenges. Each 60-foot section connected with specially designed joints rated for 4,250 tons of lifting capacity. The complete assembly would stretch nearly 3 miles from surface to sea floor, requiring materials engineering that exceeded anything previously attempted in marine operations. Wetmore selected a tapered design, thicker sections near the surface to handle maximum stress, gradually tapering toward the bottom to reduce overall weight. Every joint underwent pressure testing that simulated the crushing forces they would encounter at maximum depth. But the third breakthrough proved most revolutionary. Conventional hydraulic systems used oil-based fluid that would freeze solid under the pressure and temperature conditions at 16,000 feet. Wetmore's innovation eliminated this limitation entirely by using seawater itself as hydraulic fluid. The system would pump ocean water down through the pipe string at 750 pounds per square inch to power the capture mechanism. The ocean became the hydraulic system, an elegant solution that turned the hostile environment into an operational advantage. The seawater hydraulic concept required complete redesign of the capture vehicle's control systems. Traditional hydraulic components couldn't function with seawater, which corroded metal and lacked the lubricating properties of conventional fluid. Wetmore's engineering team developed specialized components using materials that could withstand both the corrosive effects of seawater and the crushing pressure of the deep ocean. Every valve, actuator, and control mechanism required custom manufacturing to tolerances measured in thousandths of an inch. Howard Hughes proved as revolutionary as the technology his cover story protected. When CIA officials approached the billionaire with their audacious fiction about deep-sea mining for manganese nodules, Hughes agreed instantly. His empire of private companies provided perfect operational security, no stockholders demanding explanations, no Securities and Exchange Commission oversight, no public scrutiny of expenditures that would eventually reach $800 million. Hughes's reputation for impossible ventures made the cover story credible rather than suspicious. The manganese nodule deception sparked genuine international interest in seabed mining rights. Hughes's public statements about ocean floor mineral extraction convinced competitors that American billionaires had identified profitable new resource streams. Soviet intelligence monitored the project carefully, but concluded it represented legitimate commercial mining rather than intelligence gathering. The KGB's technical assessment noted that lifting manganese nodules from deep ocean floors would indeed require the type of specialized equipment Hughes was developing. Soviet surveillance intensified as construction progressed through 1972. 2 Soviet vessels took permanent stations near Long Beach shipyard, photographing the Hughes Glomar Explorer from international waters. KGB operatives attempted to recruit Hughes's employees, offering substantial payments for information about the ship's capabilities and intended operations. But Hughes's obsessive secrecy served CIA interests perfectly. His companies routinely operated under strict confidentiality agreements that made employee discretion standard procedure rather than suspicious behavior. The fourth technological breakthrough emerged from the moon pool's requirements. Once the submarine was captured and lifted inside the ship's hull, it needed to be examined in controlled conditions away from Soviet observation. Wetmore designed a system that could seal the moon pool from the surrounding ocean, allowing the captured submarine to float in an enclosed dry dock while analysts examined its contents. The engineering required precise control of water levels, air pressure, and structural integrity while maintaining the deception that nothing unusual was happening aboard the ship. Testing began in California coastal waters during early 1973. The dynamic positioning system exceeded expectations, holding the massive ship steady in 15-foot seas. The pipe string handled test loads of 3,000 tons without structural failure. The seawater hydraulic system operated flawlessly at depths exceeding 10,000 feet. Each component had been pushed beyond its design limits and proven capable of the unprecedented mission requirements. But Soviet naval intelligence was drawing uncomfortable conclusions. Reports reached Moscow describing American deep-sea operations that exceeded any known commercial mining requirements. The scale of equipment, the precision of positioning systems, and the massive lifting capacity suggested military applications rather than mineral extraction. KGB analysis recommended continued surveillance while stopping short of direct confrontation. By late 1973, Wetmore's impossible system was ready for operational deployment. 4 revolutionary technologies had been integrated into a single platform capable of achieving what every naval engineer considered technically impossible. The Hughes Glomar Explorer could lift 2,000 tons from depths that had never been reached by recovery operations. The cover story had convinced international observers while providing perfect operational security. The only remaining question was whether miraging steel and seawater hydraulics could function flawlessly 16,500 feet beneath the Pacific Ocean, where a single mechanical failure would doom the most audacious intelligence operation of the Cold War. April 1973 brought Sherman Wetmore to the classified workshops of Lockheed Ocean Systems in Redwood City, California, where the most complex deep-sea mechanism ever designed was taking shape in sections so sensitive that each component required separate security clearances. The capture vehicle, nicknamed Clementine, represented the convergence of mechanical engineering, materials science, and hydraulic innovation pushed beyond every known limit of underwater operations. The strong back formed Clementine's structural foundation, 2 massive steel beams stretching 179 feet long and 31 feet wide, designed to distribute the enormous stresses of lifting a 2,000-ton submarine from crushing depths. Wetmore had specified the dimensions after countless calculations involving load distribution, structural integrity, and the precise geometry required to align with a Gulf II class submarine's hull configuration. The beams themselves weighed nearly 400 tons, requiring specialized transportation from the steel mills of Pennsylvania to the California assembly facility. 8 hydraulically operated grabbers mounted along the strongback's length would perform the actual capture. Each grabber consisted of articulated steel fingers designed to close around the submarine's irregular hull, while it rested on soft sediment 16,500 feet below the surface. The engineering challenge was staggering. The grabbers had to maintain precise alignment with 3 designated points on the submarine's hull while accommodating the unpredictable settling that occurred when a massive object had rested on ocean floor sediment for over 5 years. Wetmore's team had identified the critical alignment points through careful analysis of the halibut's reconnaissance photographs. The submarine's bow section offered the most stable attachment point, while the missile compartment's cylindrical structure provided secondary grab points that could distribute lifting forces without crushing the hull. But the stern section had separated from the main wreckage, complicating the capture sequence and requiring the grabbers to secure an asymmetrical load that could shift catastrophically during the ascent. The materials science breakthrough came through miraging steel, an alloy that offered incredible tensile strength but exhibited dangerous brittleness under extreme stress. Lockheed's metallurgists had tested sample components to destruction, determining that miraging steel could handle the lifting forces required for the mission while maintaining the precise tolerances necessary for the grabber mechanisms. But the trade-off was unforgiving: maximum strength for lifting capability, but catastrophic failure if any component exceeded its stress limits. The control system represented the most sophisticated remote operation ever attempted at such depths. 2 redundant 3-inch diameter electromechanical umbilical cables ran 17,000 feet through the pipe string, carrying electrical power, hydraulic control signals, and data transmission for cameras and sensors. Each cable contained dozens of individual conductors, all insulated and protected against the corrosive effects of seawater and the crushing pressure that increased with every foot of descent. Television cameras mounted throughout Clementine would provide visual feedback during the capture sequence, but the lighting requirements at such depths pushed illumination technology to its limits. Conventional underwater lighting systems failed under extreme pressure, requiring custom-designed units that could function at 750 pounds per square inch while providing enough illumination for precise maneuvering around the submarine's hull. The hydraulic system's complexity multiplied exponentially when integrated with the capture mechanism. Seawater pumped down through the pipe string had to operate dozens of individual actuators with millimeter precision while maintaining consistent pressure throughout the 3-mile-long hydraulic circuit. Wetmore's engineers designed pressure compensation systems that could adjust for the varying loads as grabbers closed around different sections of the submarine's hull. Testing began with scale models in Lockheed's pressure chambers, where 1/10 scale versions of the grabbers were subjected to simulated deep ocean conditions. The models performed flawlessly, closing around submarine hull mock-ups with the precision required for the actual mission, but scaling up to full-size components introduced variables that couldn't be fully tested until the system reached operational depth. Sea trials off the California coast in late 1973 exceeded every performance expectation. Clementine successfully lifted test weights of 3,000 tons from depths of 12,000 feet, proving the integrated system could handle loads exceeding the mission requirements. The grabbers operated with mechanical precision, closing around irregular test objects while maintaining the structural integrity necessary for controlled lifting operations. The dynamic positioning system demonstrated remarkable accuracy during the trials, holding the Hughes Glomar Explorer steady within 50 feet of target coordinates, despite 15-foot seas and variable ocean currents. The pipe string remained stable throughout the testing, with stress measurements confirming that the tapered design effectively distributed lifting forces without approaching failure limits. But Soviet naval intelligence was reaching disturbing conclusions about American deep-sea capabilities. Analysis of Hughes's mining operation revealed equipment specifications that far exceeded commercial requirements for manganese nodule extraction. The precision positioning systems, massive lifting capacity, and sophisticated control mechanisms suggested military applications that couldn't be explained by mineral extraction economics. 2 Soviet surveillance vessels had taken permanent positions near the Hughes Glomar Explorer's testing area, photographing operations and monitoring radio communications. KGB technical analysts noted that the ship's equipment could theoretically lift objects weighing several thousand tons from depths approaching 20,000 feet, capabilities that had no apparent commercial justification but obvious military implications. The Soviet surveillance created operational challenges for Wetmore's team. All testing had to maintain the manganese mining cover story while proving systems that were obviously designed for much more complex operations. Test objects were disguised as mineral extraction equipment, and lifting procedures were modified to appear consistent with commercial deep-sea mining rather than precision recovery operations. December 1973 marked the completion of Clementine's final systems integration. The capture vehicle had proven capable of lifting masses exceeding mission requirements with precision control at depths never before attempted by any recovery operation. Every component had been tested beyond design specifications and proven capable of functioning in the hostile environment of the deep Pacific. The miraging steel grabbers had demonstrated the strength necessary for lifting a 2,000-ton submarine, but metallurgical analysis revealed stress patterns that approached the material's brittle failure threshold. The engineering team calculated that the grabbers could handle the expected loads with acceptable safety margins, but any unexpected stress concentration could trigger catastrophic failure of the entire capture mechanism. As 1974 began, Clementine represented the most sophisticated deep-sea recovery system ever constructed, ready for an operation that would either prove American engineering could overcome impossible odds or demonstrate the fatal limitations of pushing technology beyond its ultimate boundaries. July 4, 1974, brought the Hughes Glomar Explorer to position 40 degrees 6 minutes north, 179 degrees 54 minutes east, where the Pacific Ocean stretched endlessly toward the horizon under overcast skies that provided perfect cover for the most audacious intelligence operation in Cold War history. At 1:01 p.m. local time, Sherman Wetmore stood in the ship's control center watching sonar displays confirm what reconnaissance photographs had promised 6 years earlier. The wreckage of K-129 rested in 3 sections on the abyssal plain 16,500 feet below. The sophisticated dynamic positioning system engaged automatically as the ship reached the target coordinates, computer-controlled thrusters adjusting thrust vectors every few seconds to counteract ocean currents and surface drift. Wetmore monitored the positioning displays with the intensity of an engineer who understood that success or failure would be measured in feet rather than miles. The submarine's remains lay scattered across roughly 400 yards of seafloor, requiring precision navigation that exceeded anything previously attempted in deep ocean operations. Soviet surveillance had intensified dramatically as the Hughes Glomar Explorer approached the recovery site. The Chazma, a Soviet naval vessel, had shadowed the Americans for 3 days, maintaining visual contact while radioing regular reports to Pacific Fleet headquarters in Vladivostok. A second Soviet ship, the SB-10, replaced the Chazma on July 2nd, bringing sophisticated monitoring equipment and a helicopter that circled the American vessel, taking detailed photographs of the deck operations. But the manganese mining cover story held perfectly under Soviet scrutiny. Hughes's public statements about deep-sea mineral extraction had convinced international observers that the operation represented legitimate commercial mining rather than intelligence gathering. Soviet technical analysts had examined manganese nodule deposits in the target area and confirmed that the ocean floor contained sufficient mineral concentrations to justify large-scale extraction operations. The pipe string deployment began at dawn on July 5th, each 60-foot section lowered through the moon pool with mechanical precision that masked the revolutionary technology beneath the routine appearance. Wetmore's tapered design distributed structural loads effectively as the assembly grew longer, but the sheer scale of the operation tested every engineering calculation. Nearly 3 miles of steel pipe, hydraulic conduits, and control cables descended into the crushing darkness while the ship's positioning system maintained station within 50 feet of the target coordinates. Clementine's descent through the water column took 4 days of careful monitoring as the capture vehicle traveled deeper than any recovery mechanism had ever operated. At 5,000 feet, external pressure reached 225 pounds per square inch, enough to crush conventional equipment. At 10,000 feet, pressure doubled again while water temperature dropped to just above freezing. At 15,000 feet, the crushing forces approached the theoretical limits of materials science. Television cameras activated as Clementine approached the ocean floor, their powerful lights penetrating the absolute darkness to reveal a landscape that no human eyes had ever witnessed. The submarine's bow section emerged from the sediment like a metallic ghost, its hull plates corroded by 6 years of exposure to seawater, but still recognizably Soviet in design. The missile compartment lay partially collapsed roughly 150 feet from the bow. While the stern section had separated completely and settled into soft sediment, the capture sequence required precision that tested every component of Wetmore's integrated system. Hydraulic actuators powered by seawater pumped down through the 3-mile pipe string began closing the 8 grabbers around the submarine's hull with millimeter accuracy. Each grabber had to align perfectly with predetermined attachment points, while accommodating the unpredictable way the submarine had settled into the seafloor sediment. Soviet observers on the surface noted unusual activity aboard the Hughes Glomar Explorer, but interpreted the operations as consistent with deep-sea mining procedures. The ship's crew maintained perfect operational security, conducting all sensitive operations within the enclosed moon pool where Soviet surveillance couldn't observe the actual recovery mechanisms. Radio communications followed commercial mining protocols, discussing equipment status and weather conditions without revealing the historic intelligence operation unfolding 3 miles below. The grabbers closed around the submarine's hull at 11:47 p.m. on July 8th, achieving mechanical contact with a 2,000-ton prize that could reshape American understanding of Soviet nuclear capabilities. Hydraulic pressure readings confirmed that all 8 grabbers had engaged properly, distributing lifting forces across the submarine structure without exceeding the stress limits of the corroded hull plates. The ascent began at 100 feet per hour, a deliberately slow rate designed to prevent structural failure of either the pipe string or the captured submarine. Wetmore monitored stress readings continuously as the combined load of Clementine and the K-129 created unprecedented tension throughout the lifting system. The tapered pipe string performed exactly as calculated, with thicker sections near the surface handling maximum stress, while the gradually reduced diameter toward the bottom minimized overall system weight. At 8,000 feet depth, telemetry confirmed that the submarine remained stable in Clementine's grasp, while 3 miles of pipe string held steady against the enormous forces involved. The impossible was happening with mechanical precision. American engineering was lifting a Soviet submarine from depths that every naval expert had declared permanently beyond human reach. Then, at approximately 8,000 feet from the surface, catastrophic failure struck without warning. The Hughes Glomar Explorer shuddered with seismic force that felt like a California earthquake lasting 10 seconds. Wetmore watched in horror as stress readings spiked beyond instrument limits before several of the miraging steel grabbers fractured simultaneously, their incredible strength proving fatally brittle under unexpected stress concentrations. Two-thirds of the submarine, including the missile compartment with nuclear warheads, guidance systems, and the cryptographic materials that had justified the entire operation, broke free from the remaining grabbers and plunged back toward the ocean floor. The stern section and most of the missile compartment disappeared into the abyss, taking with them the intelligence treasures that could have reshaped Cold War strategic planning. Only 38 feet of the submarine's bow section remained secure in the surviving grabbers, as Clementine slowly ascended through the remaining 8,000 feet of crushing water. On the surface, Soviet surveillance ships noted that the Hughes Glomar Explorer's mining operations had concluded successfully, their crews completely unaware they had witnessed the partial success of history's most audacious intelligence theft. The miraging steel that had promised maximum strength had revealed its fatal weakness at the moment of ultimate test, transforming technological triumph into devastating partial failure. August 1974 found Sherman Wetmore standing in the sealed moon pool of the Hughes Glomar Explorer as Clementine's surviving grabbers delivered their truncated prize, 38 feet of Soviet submarine bow that represented both technological triumph and devastating intelligence failure. The forward compartment had survived the catastrophic ascent intact, but the missile compartment containing nuclear warheads, guidance systems, and cryptographic materials now rested permanently on the Pacific floor, 16,000 feet beyond any future recovery attempt. The human cost emerged first as recovery teams entered the flooded bow section. 6 Soviet sailors' remains were discovered in the forward torpedo compartment, their bodies preserved by the crushing cold and pressure of the deep ocean. These men had died instantly when K-129 imploded during its final dive 6 years earlier, never knowing their submarine would become the target of the most audacious intelligence operation in naval history. CIA protocol demanded immediate analysis of the recovered materials, but Wetmore insisted on honoring the Soviet sailors first. In a classified ceremony conducted within the ship's moon pool, American naval personnel gave their Soviet counterparts full military honors. The bodies were placed in a specially constructed metal casket due to radioactivity concerns from the submarine's nuclear reactor, then committed to the sea with the same dignity accorded to fallen American servicemen. The irony wasn't lost on anyone present, enemies in life, but sailors bound by the common brotherhood of men who had chosen to serve beneath the waves. The intelligence harvest from the truncated recovery proved more valuable than initial assessments suggested. The forward compartment contained 2 nuclear torpedoes with warheads that revealed Soviet nuclear weapon design principles previously unknown to American analysts. The torpedo guidance systems incorporated technology that confirmed American strategic assessments about Soviet submarine capabilities, but also revealed unexpected sophistication in certain targeting algorithms. Navigation equipment recovered from the bow section provided crucial intelligence about Soviet submarine patrol patterns and communication procedures. Code fragments found in the ship's documentation, while incomplete without the main cryptographic materials from the missile compartment, still offered insights into Soviet Pacific Fleet operational security. Most significantly, the recovered sonar equipment confirmed that Soviet submarines operated with acoustic signatures that American attack submarines could detect at greater distances than previously estimated. But the greatest intelligence value emerged from what the recovery revealed about Soviet strategic doctrine. The K-129's patrol mission had been designed to position the submarine within striking distance of American naval installations in Hawaii and the Pacific coast. Analysis of the recovered navigation charts and operational orders confirmed that Soviet submarine-launched ballistic missiles could indeed target major American cities from mid-ocean patrol positions. But the guidance systems lacked the precision necessary for military installations, requiring accuracy within hundreds of yards. The Soviet surveillance ships that had monitored the entire operation departed with ceremonial acknowledgement that puzzled American analysts for years afterward. As Clementine approached the surface with its captured prize, the Soviet vessel SB-10 sounded its whistle 3 times, a naval tradition meaning farewell or safe journey. The Soviet crew had observed what appeared to be a successful deep-sea mining operation, completely unaware they had witnessed the partial recovery of their own submarine. Plans for Project Matador began immediately, designed to return and recover the missile compartment that contained the most sensitive intelligence materials. Wetmore's engineering team analyzed the mechanical failure that had cost them 2/3 of the submarine, determining that stress concentrations in the miraging steel grabbers had exceeded the material's brittle failure threshold by less than 5%. Minor modifications to the capture mechanism could prevent similar failures in future operations. But geopolitical events intervened before Project Matador could proceed. In February 1975, investigative journalist Seymour Hersh exposed the operation through sources within the intelligence community, who questioned the enormous expenditure for partial results. Pulitzer Prize-winning journalist Jack Anderson broke the complete story to a nationwide audience in a March radio broadcast, revealing details of the Hughes Glomar Explorer that ended any possibility of returning to the recovery site. The public exposure triggered international controversy about American intelligence operations in international waters, but also inadvertently confirmed Soviet suspicions about advanced American deep-sea capabilities. Moscow's technical analysis of the reported operation convinced Soviet naval planners that the United States possessed recovery capabilities that threatened the security of any submarine operating in Pacific waters deeper than 10,000 feet. The technological legacy of Project Azorian extended far beyond intelligence gathering. The innovations pioneered for the submarine recovery, dynamic positioning systems, deep-water heavy lift capabilities, integrated hydraulic systems using seawater, and precision operations at unprecedented depths became standard technologies for offshore petroleum drilling. The Hughes Glomar Explorer itself, decades ahead of its time, served as the prototype for all modern drill ships operating in deep ocean environments. Sherman Wetmore returned to civilian marine engineering, carrying secrets that would remain classified for decades, but also carrying the satisfaction of proving that American democratic innovation could achieve what totalitarian systems considered impossible. The partial recovery had yielded intelligence that reshaped American strategic planning for the remainder of the Cold War, confirming nuclear superiority while revealing the true extent of Soviet submarine capabilities. CIA analysis concluded that Project Azorian ranked among the most imaginative and bold operations in intelligence history, proving that American engineering ingenuity could overcome seemingly insurmountable technical barriers when national security demanded revolutionary solutions. The mission had demonstrated that democratic collaboration between government and industry could achieve results that centralized totalitarian planning could never match. The final vindication came through strategic impact rather than engineering success. The recovered Soviet technology confirmed American assessments about nuclear weapon capabilities while revealing crucial intelligence about submarine patrol patterns and targeting procedures. Most importantly, the operation proved that American engineers could achieve the impossible when challenged to serve their nation's security interests. Years later, Wetmore would reflect on the operation with quiet pride, tempered by the knowledge that mechanical failure had prevented complete success. But the patriotism and dedication of hundreds of Americans who had maintained perfect secrecy while pushing technology beyond all known limits had achieved something more valuable than intelligence, proof that democratic innovation could triumph over any challenge totalitarian systems might present. The impossible had become inevitable when American engineers refused to accept conventional limitations as permanent barriers to national security.